Good morning to all of you. Today we are going to discuss the concept is electric field. What is electric field? Had we discussed in gravitation force, gravitation field? What is meant by gravitation field? It is the space or region around a mass and influence the other masses is called gravitation field. Similar way, here also we can say that electric field means it is the space or region around a charge up to which it influences the other charges is called electric field. That means the definition will dictate later. First, we'll listen to the explanation. Electric field means it is the space or region around a charge which influences the other charges. How we can say? Suppose if you're taking two charges, Q1 and Q2. First of all, whenever you place with charge Q1, it will develop some field around it, and you are placing the other charge in the field of Q1, then Q2 will experience force in the field of Q2. Similar way, if Q2 is initially placed, then Q2 will develop some field around it. And if you're placing Q1 in the field of Q2, then Q2 will experience a force. This force is due to the interaction of the charged particles. That means if I take the third charge, Q3, then Q3 is interacted by the field of Q1 and Q2. Therefore, the net field on Q3 is due to both of Q1 and Q2. And net force is also due to the resultant of field due to Q1 and Q2 at Q3. This way, we can calculate here field. That means field is nothing but is the space or region around the charge. It can influence the other charges. Now, is it same everywhere? No. It will be different at different points. It will be different at different points. It will change. That means field is not same at all the times. That means the attractive force on Q2 is not same. Suppose here field was created by Q1 and Q2 is placed at R1, then it will experience some force. Now the same charge Q2 is placed at R2. Is it experience same force? No. Here also it will be different. Here also it will be different. It will not experience the same magnitude of force. It will experience different magnitude of force. The magnitude of force is not same for the charges placed at various points. That means the field is non-uniform. The field is not uniform. The field is not uniform. Is it clear? Yes. Then we will go for the topic. Here, electric field. What is electric field? Note in the definition. Electric field. The space around an electric charge. All of you note down. It's already there on the board. The space around an electric charge where its influences can be felt. Where its influence can be felt by another charge is called electric field. It's called electric field. Electric field means it is a space around an electric charge where its influence can be felt by another charge is called electric field. Now, electric field is said to be exist in a region in which an electric charge experiences electric force. Suppose if we are placing some charge and it is not experiencing any force, that indicates that no field is existing there. Wherever the field exists, then only the other charged particle will experience force. If no field, no force act on it. Now we are saying that field attraction, the attraction force on the other charge is not same everywhere. That means the strength of field is not same everywhere. Attracting force is nothing but strength. The strength of attracting or repelling the charge, other charge. That means it's not same. That's called is defined by a quantity called intensity of electric field. Note down the intensity of electric field definition. The intensity of electric field. The intensity of electric field or electric field strength E at a point. Electric field strength E at a point in space is defined as the force experienced by unit positive test charge placed at that point. This electric field also called as strength of electric field strength are also called as electric field strength. Suppose if I place charge capital Q, then it will have some field. Then, and I'm testing with this one test charge Q0, which was placed at R. What is the strength of the field at this point? For that one, what we'll do? First, we'll calculate the force acting on charge of Q0. The force is generally repulsive. If capital Q is positive, and test charge is always positive. Test charge is always positive. Therefore, force equal to 1 by 4 pi epsilon naught capital Q small q naught by r square. Capital Q small q naught by r square is equal to 1 by 4 pi epsilon naught capital Q small q naught by r square. Then, by definition of electric field, E bar is equal to F bar by Q naught. That means it is 1 by 4 pi epsilon naught capital Q by r square into r cap. Here r cap is the direction of the charge from the point O. Here, what is the definition of electric field intensity? It is a force acting per unit test charge is known as strength of electric field at a point. That means, be careful, what is the definition of strength of electric field? E bar equal to F bar by Q naught. That means we can calculate strength of electric field at a point by dividing with this test charge with the strength of electric field at a point. Is it clear? Then we can note down here E bar equal to F bar by Q naught. Then next phase. Now, next to note down continuation. Here, electric field strength is a vector quantity as scalar quantity. Definitely, as force is vector quantity, the field is also a vector quantity. It has both magnitude as well as direction. Then, what is the direction? Direction is nothing but the test charge is placed at one point. In what direction the test charge will experience force, the same is the direction of electric field. The same is the direction of electric field. Let me see here. Suppose this is capital Q, this is Q naught. This is always positive. Test charge is always positive. If it is positive, then what happens? This test charge will experiencing repulsive force away from the charge. Therefore, we can say here electric field also away from it. That means electric field E bar is away from charge. Away from charge. If capital Q is positive. Capital Q is positive. Now, suppose if I am considering capital Q negative and test charge is always positive. I'm repeatedly saying test charge is always a unit positive charge. It will never be negative charge. That's why here force will experience in this direction. Therefore, field also will be in this direction. That means E bar is towards the charge capital Q. If Q is capital Q is negative, do you clear? I think everyone clear? Yes. Then, what is the SI unit of electric field strength? SI unit is Newton per Coulomb. Force by charge unit is Coulomb, and the force unit is Newton. Therefore, Newton per Coulomb, and also we can write as volt per meter. Then we'll go for uniform electric field and non-uniform electric field. What is meant by uniform electric field? What is meant by non-uniform? Uniform electric field means electric field is a vector quantity. That's why it has magnitude as well as direction. That means if its magnitude and direction is not changing at every point, at every time, at every point of space, that means in the region, every point it has same magnitude of field and same direction of field, then we can say that it is a uniform electric field. And if it is magnitude changes or direction changes or both changes, both magnitude and direction are changing with position to position or in point to point, then we can say that it is a non-uniform electric field. Then what is the example for uniform electric field and what is the example for non-uniform electric field? In case of uniform electric field, suppose if you take two plates, this is positive plate and it is negative plate of equal magnitude. Then obviously the field which was developed is uniform electric field. That means what we can say, the field, the electric field which is developed between two parallel plates, E developed between two parallel plates is two parallel plates is uniform electric field. And the field which is developed due to a point charge, that is isolated positive charge, or you can consider isolated negative charge. That means for isolated positive charge, it moves away from it. The field which is produced due to isolated positive charge or negative charge is always positive. Then this is about uniform and non-uniform electric field. Now this one will come as a NCERT question. Electric field intensity due to isolated electric field intensity due to an isolated point charge. I think this was already we derived, just we are doing. See, just now I explained the definition of electric field, same thing. Now here we are considering a point capital Q. Now we are considering a charge capital Q, placed at A. And we'd like to find the electric field intensity at point B. Then to find the electric field intensity at point B, what we have to place? A test charge Q0 is placed. Test charge is always positive, which was placed there, and which is at a distance of R. Then what is the force acting on Q0 due to capital? That we know already that F equal to 1 by 4 pi epsilon naught capital Q small q0 by R square. This acts along the line joining the two charges. Then by the definition of electric field intensity, we can write E bar equal to F by Q0. That means E bar equal to 1 by 4 pi epsilon naught Q by R cap. And here already we know that if capital Q is positive, E is away from the charge. That's why in the diagram we can say as along AP bar. And if capital Q is negative, E bar is along P to A bar, that is towards the charge. Now, here in the first situation, we have explained the electric field intensity in vacuum. That means the initial charge capital Q is placed in vacuum or free space. Suppose if charge capital Q is in a medium having a permittivity K and dielectric constant K, then K equal to epsilon naught by epsilon naught. Then we have E medium equal to E free space by K. That means you can explain as in E naught is equal to 1 by 4 pi epsilon naught capital Q by R square in vacuum. Now in medium, I can write as 1 by 4 pi epsilon capital Q by R square in medium. Then we can write by definition K equal to epsilon by epsilon naught. That's why we can write epsilon is equal to K times of epsilon naught. We will get here as electric field in medium is equal to 1 divided by 4 pi times of K epsilon into capital Q by R square. Therefore, we can write electric field in medium equal to E naught by K, where E naught is equal to 1 by 4 pi epsilon naught capital Q by R square. We can write here as 1 by K times of 1 by 4 pi epsilon naught capital Q by R square. That's why we'll get this expression. That means when a charge capital Q is placed in a medium, note down this point, when a charge capital Q is placed in a medium, having dielectric constant K, then electric field intensity in medium decreases by K times. Is it clear? Okay. Now, we'll go for the next one. Some important points regarding it. Now see here, this is one thing. We have discussed the principle of superposition. Same way. Suppose there are charges are there, Q1. You can see here. This is charge Q1. It is charge Q2. And it is Q3, Q4, Qn are located at various points in space. Now I would like to find net electric field intensity at point B. Then how many fields are existing? There are n charges are there. Means due to that reason, how many fields are developed at point B? N fields are developed at point B. Therefore, as they are developing n fields, then what is the direction of each field? That means here Q1 will experience a field of E1 bar, and Q2 will experience a field of E2 bar, and it is E3 bar, and it is E4 bar, and it is En bar. N fields are there. Therefore, if N fields are there means what is the resultant fields? The sum of all the fields. Just like what we have done in electric force, net electric force. This is also called as principle of superposition. We will use this concept when more than two charges are there means two charges are there if they are asking net electric field at any point. Okay. Next. Now come to the second point. Next point. If E bar is the electric field at a point and charge Q is kept at that point such that force acting on that charge is F bar, we can write F bar equal to Q times of E bar. Suppose here capital Q is there at home. Now at point B the electric field is E bar. Is it clear? E bar is the strength of electric field at point B. Suppose if I place charge Q at that point, then what happens? The force acting on the charge F is equal to Q into charge of that field into charge at that point into electric field. F bar equal to Q into E bar. F bar equal to Q into E bar. Suppose if this Q is positive, if Q positive, F bar equal to Q times of E bar. Then if I say if this Q is negative, then what happens? F bar equal to minus Q times of E bar. Then we can say that force and electric field are acting in same direction. Force and electric field are acting in same direction if Q is positive. And electric field is acting in this direction and force will act in this direction when the force is acting opposite to it. When force is acting opposite to it, both are acting opposite, then when charge is negative. That's why I have given if Q is positive, F bar equal to parallel to E bar, and if Q is negative, F bar is anti-parallel to E bar. Next point. Suppose